In this video, we are going to find the analogy between the plug flow reactor and batch reactor. And we will declare that all the solutions that are developed for a batch reactor are going to be valid for a plug flow reactor where no constraints other than the kinetic considerations are present. So let us start from the situation where we have dn sub a over dt 1 over v is equal to r sub a, simplifying to dca over dt. Remember that we had this for the situations where epsilon is 0. Epsilon can be 0 for net stoichiometric coefficients being equal to 0, or epsilon is irrelevant for incompressible flows. So let's derive the expressions for a plug flow reactor. In a plug flow reactor, we now have fluid coming in and going out into a differential volume element, Fa at z, Fa at z plus delta z, or equivalently we can write Fa at v and Fa at v plus delta v, where z is the axial coordinate, v is the volume coordinate. If the cross-section is not changing, volume can be used easily. So we are going to write our balance equation under steady-state conditions to obtain dFA over dV to be equal to R sub A. And here our Fa is Ca times volumetric flow rate. Now this volume change expression is going to enter into the picture both in here and in here. So Ca is going to be Ca0 times 1 minus x divided by 1 plus epsilon x and volumetric flow rate will be the same expression as the volume. It will be V0, volumetric flow rate at the inlet, times T0 over T, P over P0, times 1 plus epsilon x. Again, we are going to approximate for the conditions where temperature change and pressure change can be approximated to 1. V volumetric flow rate at any position in this reactor is going to be V0 1 plus epsilon x. And of course, we have to take this term also into consideration. V is equal to V0. Let's just leave temperature and pressure dependencies out, 1 plus epsilon x, then dV is equal to V0 epsilon dx. Now we have expressed everything in terms of the volume change parameter and conversion. So for the concentration term that is going to be expressed in Ra, we have a concentration expression in terms of x, and for the volume term we have a volume change taken into consideration in terms of the initial volume times the volume change.